Okay, so this is going to be the most beautiful proof I've ever seen. And it is to this question: how many spaces are created by n intersecting lines? And we're not going to allow more than 2 lines to intersect at any specific point. So like that is good, but then if we did that, or like they're all at the same point, that's a no-no. So here's what we're going to do. We're going to make ourselves a lovely little graph or table. I know words. That's Baby Seal. I assure you that he's fine. He's just gonna try and convince all of us that he is suffering greatly because he's on a diet. I assure you he's okay. So we're gonna make lines, intersections, and spaces created. So here's our paper, and right now we have 0 lines, which obviously means we have 0 intersections. And right now we're gonna focus a little bit on the intersections. If I were to change this, and now I'm going to give us a line. Okay. Now we have 1 line, and there are still 0 intersections. We can also go ahead and start filling in some of this spaces created. With 0 lines, 0 intersections, there was a single space. With 1 line, there are 0 intersections. But there are now 2 spaces created. If we go on, we keep going, we're gonna have 2 lines, and I'm gonna say some kind of perhaps obvious things here, but notice that my second line crossed my first line, which means that I now have 1 intersection. And we now have 1, 2, 3, 4 spaces created. If I add a 3rd line, so I'm gonna line up my ruler so I can add a 3rd line. And I should have probably also stated that we're stipulating here that every line has to cross every other line. So if I add a 3rd line here, I'm gonna end up crossing both of my other 2 lines, which basically means I'm gonna be adding 2 intersections. So I'm gonna take this number and I'm gonna add the number of lines that I'm crossing. So I'm gonna end up with 3 intersections. And then when we have 3 lines, we're gonna add those again because we're gonna have, my new line is gonna have to cross this, and then we're gonna have 6 intersections with 4 lines. So let's just go ahead and test that real quick. So obviously I crossed my other 2 lines, and now I have 3 intersections, and I have 1, 2, 3, 4, 5, 6, 7 spaces that have been created. And if we add 1 more line, where am I gonna do that? I'm gonna do it right here. There's a reason why I'm spacing them out like I am, I promise. This line crossed 1, 2, 3 lines, so that gave us our total of 3 more intersections. You can even think about it like +3, +2, +1, +0, whatever. And it has given us more spaces. But I don't want to get too far into that. So I want to focus right now again on the intersections. And really what we're seeing is that we're adding the same, like the number of lines before. So to get the next one, we're going to add 4, and that's going to get us 10. And this is actually, you might start recognizing these are the triangle numbers. And there's a formula for the triangle numbers, which is beautiful in and of itself. But that formula is n times n plus 1 divided by 2. But that doesn't quite match up for us here, because if we plugged in 1 here, we'd get 1 times 1 plus 1 is 2. So we'd have 2 up here divided by 2, and that gives us 1, which is no good. So really what we need to do is we need to subtract 1 from each of these. So really the formula we're going to use for this is going to be n minus 1 times n minus 1 plus 1, all divided by 2. Or, because these will simplify themselves out, we're going to get, for the number of intersections, our formula is going to be n minus 1 times n over 2. So if we wanted to go and figure out 14 intersections, we could plug in here 14 minus 1 is 13 times 14 over 2 is 7. 13 times 7, that would get us the number of intersections we have with that many lines. that's going to become important in a second. Because again, the question we're asking is how many spaces are created by n intersecting lines. And this is where we get to the most beautiful proof I've ever seen. So this was something I learned in college, and I remember sitting in the class and my mind just being completely blown. So here's what we're gonna do. We're gonna have, how many lines is this? This is 1, 2, 3, 4, 5. Let's get 6 lines in here. I think that'll make me happy. Okay, cool. So here's the suggestion, because we have all of these different spaces and we can count 1, 2, 3, 4, 5, etc. But it gets kind of hard to count and it's sort of awkward. And here was the idea, was that you look at this and we know that we can count the intersections. We just figured that out. The number of intersections is going to be how many lines minus 1 multiplied by the number of lines divided by 2. That's going to get us the number of intersections. And so I can count all of the intersections, but there's other spaces that aren't quite counted, right? So like, here's the suggestion, is that you consider the lowest point in an intersection. So like for this space, right, or lowest point, vertex in a space, I guess. For this right here, I'm gonna consider that, and then that intersection can account for this space. For this space right here, this intersection can account for this space. And for this space right here, even though it has this intersection and this intersection in it, the lowest point, this one is going to account for that space. And then you're not going to double count any of your spaces. So what we think about is we think about a rectangle that is big enough to encapsulate all of our spaces. And if you have 10,000 lines, it doesn't matter. You just imagine a bigger rectangle. You just kind of zoom out and you get to see all of the intersections. So now we've got all of the intersections here in our rectangle. So it's gonna be kind of like, and then the number of intersections that we have will count almost all of the spaces. But you say, Annie, it's not counting all of the spaces, and you're totally right, which is why here is how I'm going to draw my rectangle. I'm gonna draw my rectangle like this. And I'll make it much prettier later on. So inside this rectangle that I've just added, all of my intersections are there, right? All of the lines are straight, so they're going off, and I have all of my intersections inside this rectangle. And if I consider the lowest vertex in any given space, that will count most of my spaces. But you're like, but Annie, this space right here, its lowest space is not an intersection, so it's not getting counted. And that's where this bottom line comes in and is a beautiful idea. Because you'll notice I drew my rectangle so that all of the lines intersect my bottom line. So I've got 1, 2, 3, 4, 5, 6. And those create 7 spaces. So there's a space here, space here, space here, space here, space here, space here, and space here. And so all of the other pieces in here are counted by their lowest vertex, right? This space is counted by this lowest vertex. This weird little space counted by this lowest vertex. This weird little space counted by this lowest vertex. Oh, we've got, there's like a tiny little thing happening here. I'm gonna have to redraw one of those lines, but that's okay. This tiny little space would have this vertex. All of those spaces would get counted. And then on the bottom, to count all of the spaces that aren't counted, we just have to make sure that we've intersected all of the lines with our bottom line. And then there's going to be, in 6 spaces, or 6 lines, there are 7 spaces that are created. So the way that we can count this is we can take our number of intersections right here, and we can add to this the number of lines plus 1, and that will count all of our spaces. And I just love this image of like a glowing bit coming from the bottom vertex, and then the bottom line kind of accounting for everything else. I think it's just the most beautiful thing in the world.